Okay, this is example 2 in your book section 4.2. So again, you're more than welcome to read the example in the book, but if you need to fill in maybe some gaps, I'm going to go ahead and work out the problem. So notice that this is a non-homogeneous linear second order differential equation, right? Because it's not equal to 0. Right, our first example was homogeneous, but this one's non-homogeneous. It's obviously, right, an IVP because we have initial conditions. So we can definitely apply the Laplacian operator, right, or the Laplace transform of both sides. So the Laplace transform, right, our cursive L of x prime, and I'm just going to go ahead and write it in. Okay, so the property of linearity, right, allows me to take the Laplace transform of the second derivative, plus, right, I can take my constant out, times the Laplace transform of x. And it, well, I mean, well, let me go ahead and just write this out again. So Laplace of sine 3t. Okay, so now we can we can definitely use our table. So again, on page 271 of your book, do we have a sign of kt? And we definitely do. It's k over s squared plus k squared. So I definitely know that this guy is, and my k, right, is 3. So it's 3 over s squared plus 3 squared, which is 9. And we know this guy, right? And actually this one has no derivative, so it's just going to be chi of s. So I'm going to go ahead and let's see, write this in. So 4 times chi of s, and of course because I write very big, I'm missing this part right here. So continue. So the Laplace transform of x double prime, again, I'm just looking at your equation 5 in the book. And that is, right, this guy is s squared times chi of s minus s times x of 0 minus x prime of 0. And then we just have our usual, our information that we already obtained. Okay, so I'll move this up. And this is really nice because our initial conditions, right, these guys are all 0, so that's gone. So we're just left, see, so on the left-hand side we have s squared plus 4, right? We can definitely factor out a chi of s. And we have 3 over s squared plus 9. And if we solve for chi of s, right, we want to solve for chi of s, or capital F of s, because we're going to want to take the Laplace inverse transform. And so what do we have? 3 over, so s squared plus 4 times s squared plus 9. Okay, again, our goal is to find x of t, small x of t. But right, just from our steps, we usually get our x of, or chi of s first. And we're going to use partial fractions here. But I want you to understand why you're going to use partial fractions, not just because you got to follow the algorithm. But you want to use partial fractions because if this is our, again, our capital F of s, if you want to think of it that way, and we don't see this expression in the table. But if we break this up, again, anytime you have a complicated expression and you don't know how to work with it, we'll break it up into pieces that you know how to work with, that you're familiar with. So we can break this up into expressions that may have, right, a Laplace transform associated with it. So that's, again, why we're using partial fractions. So this guy, this is actually a very good problem. This is, I'm going to move this here because I write really big. 3 over s squared plus 4 and s squared plus 9, right? Usually you want to break it up into a sum. And we want to write, usually a and our b. And notice our factors, right? These guys, these polynomials are not factorable, right, over the real numbers. Right, they're not a difference of 2 squares, they're a sum of 2 squares. So we can't factor these out, again, in real numbers. over imaginary numbers is a different story. And then we have s squared plus 9. Now, this is a quadratic factor. Well, both of these are quadratic factors, right? Because they're not linear factors because the degree of the polynomial is 2. So usually if the degree, we've been doing like s plus 3, and I think in the last one, and usually we write a on top because the degree in the denominator is 1, and a constant is usually times, x to the 0. But this is a quadratic factor, so I need to add maybe, let's see, s, and well, in this case, let me just go ahead and erase it. But I wanted to write the a and b because that's what you're usually going to write. And let's see, get my eraser here, which is not letting me erase. Okay, so I'll just cross that out. And so this is going to be a times s plus b, right? That's a linear factor. And cs plus d, that's your other linear factor. Again, we have linear over quadratic, linear over quadratic. And so now let's find our a, b, c, and d. And again, we can multiply this by the LCD. We're going to get 3 equals, so we have as plus b times s squared plus 9 plus cs plus d, that's a c, s squared plus 4. And again, I really want to emphasize this: linear factor, quadratic factor, linear factor times a quadratic factor. And I'll go ahead and stop here, and I'll continue in the next video just so it won't be too tedious.